So the final case is similar to the previous one we have just discussed. This time, however, we have a weak base being titrated with a strong acid. Okay, so for this one, we have this time the acid in the burette. Okay, and again, that acid is a strong acid. Okay, and this time in the Erlenmeyer flask, um, the analyte is the weak base. So let's say, for example, let's consider this titration curve in which ammonia, 25 ml of 0.1 molar ammonia is being titrated with 0.1 molar hydrochloric acid. Okay, again, there are four regions of interest that we're looking at. In the initial pH region, in which we have not added any hydrochloric acid to the ammonia yet. Since this time ammonia is basic, okay, then the pH of the solution in the Erlenmeyer flask should actually start relatively high at a basic level. Okay, now, however, if we were to compare this though with the titration of a strong base with a strong acid, let's say sodium hydroxide with hydrochloric acid, then we would have seen a higher start of initial pH value. Okay, as we add hydrochloric acid into this solution in the Erlenmeyer flask, the hydrochloric acid, particularly the hydronium ions from hydrochloric acid, are being consumed, okay, by the ammonia in order to produce the ammonium ions, which is acidic. That's why you actually see a lowering in the pH. Okay, but at this point, since you're producing ammonium and there still is some ammonia left over, you have a buffer again. Okay, so there are interesting points in this buffer again, such as again the pH at half the equivalence point, which we will look at later. Okay, and then when the acid fully consumes the base ammonia, okay, that is, there will be no more ammonia in solution. Instead, there will be only ammonium ions at the equivalence point. Okay, now since ammonium again is acidic, then the equivalence point is expected to be at acidic values. Okay, that's why the pH here, the equivalence point, is slightly over 5. And then past the equivalence point, wherein you're adding an excess of hydronium ions from hydrochloric acid, the pH starts to drop even faster. Okay, well past the equivalence point at which it plateaus when you have too much excess acid. Okay, but as you can see, this is slightly similar to case 2, wherein the jump from 24.9, okay, to the equivalence point 25.0 ml up to 25.1 is actually less steeper than it were if you have a strong acid with a strong base or a strong base with a strong acid. Okay, but let's calculate, let's do some math and work on this problem. What if you have hydrazine, another weak base, and you titrate it with a strong acid, nitric acid? Okay, so let's just draw what we have here. So if this is the burette, okay, since we are titrating hydrazine with nitric acid, so the nitric acid should be in the burette, that is the titrant, okay, and then in the Erlenmeyer flask is the hydrazine, okay, so H2 and H2. Okay, so before you add any nitric acid, okay, at the very beginning you only have hydrazine in the Erlenmeyer flask. Okay, so since hydrazine is only present, okay, only hydrazine, which is, remember, a weak base, is present. Okay, so since it's a weak base, we can write a nice table for hydrazine to determine the concentration of hydroxide ions that it produces. Okay, So H2 and H2 plus water, which gives you the hydrozonium ion. Okay. So it just means one proton plus hydroxide ions. Okay, and then that's initial change equilibrium. Okay, so we originally start with 0.100 molar of hydrazine, we ignore water, and then we assume that there's 0 of hydrozonium ions and 0 of hydroxide. Okay, and then a change in X at equilibrium, and then at equilibrium the concentration should be 0.100 minus X for hydrazine, X for hydrozonium, and then X for hydroxide ions. Okay, and then from here we can actually write a Kb expression. So we're given the Kb of hydrazine. So that will just be Kb, okay, is equal to 3.0 times 10 to the negative 6 is equal to the concentrations of the products. So hydrozonium times hydroxide, which are both X, divided by the concentration of hydrazine at equilibrium, which we can assume is just roughly equal to the initial concentration. So we assume that X is negligible. Okay, and if we do that, we get an X value which is equal to 5.5 times 10 to the negative 4. And keep in mind that this value is equal to the concentration of hydroxide ions. Okay? And if we plug that in the formula for POH, POH should just be negative log of that hydroxide ion concentration. So that should be negative log of 5.5 times 10 to the negative 4 molar. Okay. That should give you 3.26. Okay. And then subtracting that from 14 to get the pH, we get 10.74. Okay. Now let's move on with letter B. Okay. For letter B, how about if you have added to ammonia 20.00 ml of nitric acid. Okay, so at this point, the H plus from nitric acid will react with hydrazine, okay? Meaning the proton from nitric acid will react with hydrazine, okay? So we need to write first an ICF table. So millimoles, and then we start with hydrazine, okay? Hydrazine will be consumed by the proton from ammonia, which will just give us the hydrozonium ion. Okay, giving it enough space because I want to write a lot of things. Okay, and then it's an ICF table. Okay, so we begin first with the number of millimoles of hydrazine. So that's equal to 100 times 0.100 molar. That's going to give you 10.0. Okay. For the concentration, or rather millimole of the proton, so we have 20.00 ml. Okay. And then multiply that with 0.200 molar. Okay. What we get here is 4.00 millimoles. Okay. And then we begin with no millimoles of hydrozonium. Okay. So you can see here the acid H plus is the limiting reagent. So this will be minus 4.00 minus 4.00. This will be plus 4.00. Okay. And then this will end up to be 6 millimoles of hydrazine left. No, nothing left of H plus, and then we have 4 millimoles of hydrazonium ion produced. Okay, and then now that we have millimoles, and now that we also know the total volume of the solution, we can determine what the molarities are of hydrazonium and hydrazine, and then plug that in the Henderson-Hasselbalch equation. Okay, so that should just be pH is equal to negative log of the Ka for hydrazonium, but we're not given that value. However, we are given the value for the Kb of hydrazine. So therefore, this is just 1.0 times 10 to the negative 14, okay, divided by 3.0 times 10 to the negative 6. So let's make a side note here again that this is the Ka for H2 and H3 plus. Okay? And then that will be plus log of the concentration of hydrazine divided by the concentration of hydrazonium. Okay. So if we do this, we're gonna get for this value, this is actually gonna be negative log of 3.3 times 10 to the negative 9. Okay, which will, and then for this one will be plus log of, again, to substitute for concentrations. Let's start first with hydrazine. So that is 6.0 millimoles. Okay, divided with the total volume, which is 100 plus 20 ml. Okay, that will give us molarity, and then divide it by, again, 4.0 millimoles divided by, again, the total volume plus 20.00 ml. Okay, and we've seen this before already, wherein we can actually cancel these, and again, for the ratio of the concentration of hydrazine to hydrazonium, their millimoles, number of millimoles, can actually proxy for that. Okay, and what we'll end up with is equation. Let's get things out of the way. So what we'll get will therefore be pH is equal to the negative log of 3.39, 3.3 times 10 to the negative 9 is 8.48. Let's use that number again, okay? So let's just remember that. Plus log of 6.0 divided by 4.00. This will just be equal to 8.48 plus 0.18, okay? And this will just give you a pH of 8.66, okay? And again, at this condition, note that the pH is actually greater than the pKa, okay? And remember that this is the point at which the concentration of the weak base, hydrazine, is actually much greater than the concentration of its conjugate acid, hydrazonium. Okay, and then next, we are going to work with letter C. So what if you have plus 25.00 ml of nitric acid? Okay. So again, H plus from nitric acid will react with hydrazine. So let's write an ICF table. Okay. So we already know what the initial millimoles of hydrazine is. We're not again going to um, begin with how much hydrazine is remaining. We're assuming that this is a separate flask, okay, when we do the calculations. So this is also 10 millimolar, or millimoles rather. And then this one will be 25.00 ml times 0.200 molar, which is equal to 5 millimolar, okay, and then nothing of hydrazonium. Again, H plus is still the limiting reagent, so minus 5.00 minus 5.00 is 5.00, and this will end up to be 5.0. This one will end up to be 0, and this one will be 5.00. Okay, so therefore here the pH of the solution should be 8.48, that's pKa. We have calculated already, plus log of 5.00 millimoles, okay, for hydrazonium divided by 5.0, or for hydrazine rather, not hydrazonium, then divided by 5.00 millimoles from hydrazonium, okay? And again, these terms will cancel each other out, and the log of 1 is just equal to 0, so this entire thing actually is just pH is equal to pKa, okay? So here again, pH is equal to pKa, which means that we are at half the equivalence point, okay? And that also means that the concentration of the weak base, which is hydrazine, okay, is equal to the concentration of its conjugate weak acid, hydrazonium. All right. And then past that half the equivalence point, we have letter D, wherein we have added a total of 40.00 ml. Nitric acid. So at this point, again, the proton from nitric acid will still react with hydrazine. So another ICF table. Okay, so this is once again 10.0 millimoles, and then for the millimoles of the protons, we have 40.00 ml times 0.200 molar, which is just going to give you 8.0 millimoles. Okay. And then this one is 0, okay? Still the initial concentration, or sorry, still the limiting reagent is H plus. So this will be minus 8.00, it will be fully consumed, minus 8.00, and this will be plus 8.00. Okay. This one will end up to be 2.0, 0, and this will be 8.00. Okay? Then we can solve for pH again, which is pKa 8.48. Okay, plus log of number of moles of hydrazine, which is 2.0 millimoles, divided by the moles of millimoles of hydrazonium, 8.00 millimoles. Okay, and then we get here 8.48 plus negative 0.60. So that's just equal to 7.88. Okay. Now at this point, pH is actually less than pKa. Okay, which means that this time the concentration of hydrazine, okay, is less than the concentration of hydrazonium. So we now have more hydrazonium than hydrazine. All right. And then we now go to what if we add 50 ml of total nitric acid, or a total of 50 ml nitric acid. So again, just write an ICF table. Okay. All right, so we begin again with 10.0 millimoles of hydrazine. Okay, from H plus, that will be 50.00 ml times the concentration is 0.200 molar. Okay, so that's actually also 10 millimolar or millimoles. Okay, and then this is 0. So both hydrazine and the proton will fully consume each other. In other words, we are at equivalence point wherein we don't have any hydrazine anymore at the end of the solution, and what we are left is the hydrazonium ion. Okay, so all of the hydrazine has been converted into hydrazonium. So to determine what the hydronium concentration is as a result of the hydronium or of the hydrazonium ion hydrolyzing in water, we have to write an ice table. Okay, so that should be hydrazonium. And when it reacts with water, water will serve as the base. Okay, to produce H3O plus hydrogen. Okay, then I see. Okay, now the concentration here of hydrazonium should be 10 millimoles. Okay, 10.0 millimoles divided by the total volume of the solution this time is 100 ml from well, what used to be hydrazine plus 50.00 ml. It's the total volume now. Okay, and this will be equal to 0.0667. Water, ignore. And then we have here for hydronium 0 and 0. Okay, change in x, change by x, and then we also have the change by x here. Okay, so that at equilibrium this is 0.0667. Okay, and then we have here x, and we have here x. Let's just assume that this is equal to, or well, 0.0667 minus x, which we can assume to be just 0.667. Okay, wherein basically x is negligible. We've actually calculated already for the value of Ka. Okay, we did that here in B. Okay, this is the value of Ka of hydrazonium. Okay, so that's 3.3 times 10 to the negative 9. So we can write an expression for Ka therefore. So Ka is equal to 3.3 times 10 to the negative 9 is equal to concentration of the products at equilibrium x times x. Okay, divided by 0.0667. Okay, further simplifying that, we have 2.2 times 10 to the negative 10 is equal to x squared, wherein x is just equal to 1.5 times 10 to the negative 5. And remember, this is the concentration of the hydronium ions. Okay. Now, you can check whether our assumption was correct using the 5% rule, but I'm not going to go into that. Okay. And then we next calculate for the pH by just taking the negative log of that value. Okay. Negative log of 1.5 times 10 to the negative 5. So that should be equal to 4.82. And now at this point, again, check. So at the equivalence point, the only species which should be in solution should be the hydrozonium ion, which is acidic. And if your pH here is not acidic, then it's time to revisit the math. Alright, then for the last case, or the last volume that we want to calculate that, what if we have so far added a total of 100 ml of nitric acid? So this is way past the equivalence point. Okay, again, we can still write an ICF table. So H2 plus H plus, to get hydrozonium ions. So we begin here again with 10 for hydrazine, and then for the protons we have here 100.00 ml times 0.200 molar. This will be equal to 20 millimoles. This one should be 0. Now this time hydrazine is the limiting reagent, so it will be, well, at this point it has been fully consumed. Okay. And then we will end up with no hydrazine. We have around 10 millimoles of H plus and around 10 millimoles as well of hydrozonium ions. Now this is past the equivalence point, and notice that again we have an excess of protons along with hydrozonium ions forming. Now we assume that the amount of hydronium ions contributed by hydrozonium will be negligible, will be minimal, as we have actually calculated here. I mean, it's not the same volume, but notice that this value is very small. So if we have a higher volume here, then that concentration of hydronium ions from hydrozonium should be much smaller. Okay? And therefore, the pH of this solution should just be dependent on the concentration of hydronium ions in solution. Okay, so this will just be H is equal to the negative log of the hydronium ion concentration should be 10.0 millimoles divided by the total volume of the solution, which at this point is 100.00 from hydrazine plus 100.00 from the total nitric acid added. So this will just give you negative log of 0.0500 molar, and that's just equal to a pH of 1.30. Alright.